Welcome to Educator.com. Today's lesson is on compound inequalities. Beginning by defining a compound inequality. A compound inequality consists of two or more inequalities, and these inequalities can be joined by either the words and or. And they're handled differently depending on whether or not they're joined by the word and or. So we're going to break that down. First, discussing inequalities that are combined by the word and. If the inequalities are combined by the word and, the compound inequality is true if and only if each inequality is true. In other words, what we're looking for is the overlap or intersection between the two solution sets. So setting aside inequalities for a minute and just talking about this intersection or overlap between solution sets. Let's say that I have two solution sets. And in my first solution set, I have the numbers 1, 2, 3, 4, 5, and 6. Then I have another solution set. And in this one, I have -3, -2, -1, 0, 1, 2, and 3. If I'm looking for the intersection between these two solution sets, I'm looking for the areas where the solution sets overlap. And I look at this one and I look at this one and I see which elements are the same. And I see that I have a 1 in both of them, a 2, and a 3. Therefore, the intersection between the two, or area of overlap, would be 1, 2, and 3. When you are working with inequalities combined by the word and, this type of compound inequality, what you are looking for is this, the overlap. Because in an overlap, then the solutions you end up with will allow each inequality to be true. And just to give you an example, I may have one solution set with an inequality where I come up with a compound inequality joined by and, where I come up with x is less than 5. I may come up with for my second inequality, as part of this compound inequality, a solution set that says that x is greater than 1. So here, looking for the overlap between these two regions, I could look on the number line, 0, 1, 2, 3, 4, 5. This is telling me that x is less than 5. This one is telling me that x is greater than 1. Well, the region of overlap, the intersection, is between here and here. So this region, open circle at 1 all the way to open circle at 5, would be my solution set for a compound inequality. A compound inequality would be telling me that I have to meet these restrictions and I have to meet these restrictions. And when you see a compound inequality, an example of what it may look like would be something such as 2x plus 5 is less than 7 and 3x is greater than or equal to 2. So I have to be able to satisfy both of these inequalities to satisfy the compound inequality. If the inequalities are combined by the word or, it's handled differently. If the inequalities are combined by the word or, the compound inequality is true if and only if one or more of the inequalities is true. So what this is telling me is that the solution set is the union of the two sets. I'm looking for, instead of the intersection of the two sets, the union of the two sets. This will include elements or members of either set. So the solution set for this is going to include all the whole solution set for the first inequality, the whole solution set for the second inequality, and some of those may overlap. Some of those may intersect, some may not. Some elements may not, but they're all included. For example, let's say I have two solution sets. One is 1, 2, 3, 4, 5. And I said it can be this 1, 2, 3, 4, 5, or 3, 4, 5, 6, 7. Well, that means that I'm going to include elements that are in this one, that are in this one, and that are in both. I could rewrite that, saying, okay, I've got a 1. I don't need to duplicate things. I've got a 2. Well, I have a 3 in both. So I'm just going to write 3 one time. I have a 4 in both. 5 in both. And this one also contains 6 and 7. So when we talked about compound inequalities joined by the word and, I only included that area of intersection. I only included elements that were in both. Now, when compound inequalities are joined by the word or, then I'm going to include elements of both of the sets. They just need to be in one set or the other set, or they can be in both. Looking at examples, applying this to examples. I'm being asked to solve the compound inequality given up here. The way I'm going to go about this is I'm going to solve one equality, solve the other inequality, and then I'm going to find the area of overlap between the two solution sets. So I just solve as usual, starting out with the first inequality. 2x minus 3 is less than or equal to 6. I use my regular techniques. Here I'm going to add 3 to both sides. That's going to give me 2x is less than or equal to 9. Dividing both sides by 2. That gives me x is less than or equal to 9 halves, which is also the same as saying x is less than or equal to 4 1/2. Okay, this was my first inequality. Next, I need to solve the other inequality. Then I can start looking at the solution sets that I came up with. 3x plus 6 is greater than or equal to 12. Subtracting 6 from both sides. And then dividing both sides by 3. Noting that I was dividing by a positive number, so I don't have to worry about reversing the inequality symbol. I'm going to come up with x is greater than or equal to 2. So what this compound inequality is telling me is that I have got to meet the restrictions for x, that x is less than or equal to 4 1/2, and x is greater than or equal to 2. This type of thing is very helpful to visualize using the number line. So if I have 0, 1, 2, 3, 4, 5. Over here, I know that x has to be less than or equal to 4 1/2. So 4 1/2 is going to be about here, and it's going to be a solid dot since it includes equal to. This is the solution set for this inequality. The solution set for the second inequality is that x is greater than or equal to 2. Solid dot greater than. The area that meets the condition for both of these is the area greater than or equal to 2 and also less than or equal to 4 1/2. So what I'm going to end up with is, in red, is my solution set for this compound inequality. I could write this slightly differently by putting x in the middle, seeing that there's some redundancy there. I don't need to write x twice, and then I can actually eliminate the second x and the word and. So showing you what I mean. X is less than or equal to 4 1/2, and x is greater than or equal to 2. Instead of saying x is less than or equal to 4 1/2, I'm going to put the 4 1/2 over here. So 4.5 is greater than or equal to x, and x is greater than or equal to 2. Well, I don't need to repeat the end. So instead, I could just write this slightly differently. I know that I want x to be greater than or equal to 2. So here's 2. X is going to be greater than or equal to that. And x is going to be less than or equal to 4.5. So x is going to include these two values and everything between. So you can certainly write it like this or like this. Those all say the same thing, but the simplest, clearest way to write it is to just write it all together, not repeat the x, and say x is greater than or equal to 2 and x is less than or equal to 4.5. So again, the overall technique was to solve the first inequality, solve the second inequality, and then look at my solution set and realize that the solution set for the entire compound inequality would have to meet both of these restrictions, would have to include elements that are found in both solution sets. For the second example, I'm solving another compound inequality. Again, taking the first inequality. 4x minus 6 is less than or equal to 10. Adding a 6 to both sides. That's going to give me 4x is less than or equal to 16. Dividing by a positive number, so I'm not having to worry about flipping that sign around. And that gives me x is less than or equal to 4. For my second inequality, I have 5x minus 2 is greater than 23. Adding 2 to both sides gives me 5x minus 2 plus 2 is greater than 23 plus 2. So that's 5x is greater than 25. Divide both sides by a positive number, so I'm fine with the symbol here. Dividing both sides by 5 yields x is greater than 5. So this compound inequality is saying I have this inequality and I need to meet the conditions for this inequality as well. So my solution set is that x is less than or equal to 4 and x is greater than 5. Well, let's look at this on the number line. 1, 2, 3, 4, 5, 6. Okay. X is less than or equal to 4. So x, this first inequality, here's the solution set graphed out. My second one says that x is greater than, so open circle, greater than 5. What I need is the area of overlap between the two solution sets. But there is no area of overlap. If there is no area of overlap, there is no solution set for this. This does not work, so my solution set is the empty set. Because x cannot be less than or equal to 4, and then at the same time also be greater than 5. So this is the empty set. In the third example, I have a compound inequality, and this time I'm going to have to really look at it and understand that they didn't use the word and, but the way it's written is implying that the word and is there. It means the same thing. What they're saying is that this entire expression, 3x minus 2, is greater than negative 4, and it's also less than or equal to 7. So to just make it clear, I'm going to separate it out into two inequalities. My first inequality is that negative 4 is less than 3x minus 2. Okay, so that is my first inequality. My second inequality is over here, and that is 3x minus 2 is less than or equal to 7. So this means the same thing, just writing it out a longer way than up here. And it means that they are combined by the word and. Solving this inequality over here by first adding 2 to both sides. Adding 2 to both sides, which is going to give me negative 2 is less than 3x. Dividing both sides by 3. Negative 2 divided by 3 is less than 3x divided by 3. So it's negative 2/3. Negative 2/3 is, that should be a 3 right there, is less than x. Okay, so negative 2/3 is less than x is the solution set for this first inequality. For the second inequality, I'm going to add 2 to both sides. Which is going to give me 3x is less than or equal to, oh, that's actually 7. Mistake right there. Okay, so 3x minus 2 is less than or equal to 7. So this on the right, that is a 7. So what I'm going to do is go ahead and fix that right there. 3x minus 2 plus 2 is less than or equal to 7 plus 2. So I have 3x is less than or equal to 9. Now I'm going to divide both sides by 3. Is less than or equal to 9 divided by 3, which is going to give me x is less than or equal to 3. My solution set for the compound inequality is that x is greater than negative 2/3 and it's less than negative, less than or equal to 3. Less than or equal to 3. Making this a little bit simpler, we can eliminate the x and the end and come up with negative 2/3 is less than x and x is less than or equal to 3. On the number line, I could show that as negative 2, negative 1, 0, 1, 2, 3. Negative 2/3 would be right about here. I'm going to use an open circle. And 3 is right here. It's going to be a closed dot. And the solution set does not include negative 2/3, but it does include 3 and everything that lies between. So for my compound inequality, I first needed to break it out into these two inequalities. Negative 4 is less than 3x minus 2, and 3x minus 2 is less than or equal to 7. Then I solved the inequality on the left and got that x is greater than negative 2/3. I solved the inequality on the right and saw that x is less than or equal to 3, and I simply wrote that as x is greater than negative 2/3, but it's less than or equal to 3, and represented it on the number line as well. In this next example, we're working with a compound inequality joined by the word or. So the solution set for this will include the elements in the solution set of the first inequality, second inequality, and those that are actually in both inequalities. Starting with this first inequality, negative 3x minus 7 is greater than 8. Solving that, I'm going to add 7 to both sides. That's going to give me negative 3x is greater than 15. That's a 7. Then I'm going to be dividing by a negative 3. Since I'm going to be dividing by a negative 3, I need to reverse the inequality symbol. So I reversed that and made the greater than symbol a less than symbol because I'm dividing by a negative number. Negative 3's drop out, and I end up with the inequality x is less than negative 5. So that is my first inequality. My second inequality, negative 6x plus 8, is less than or equal to negative 10. Subtract 8 from both sides. The 8's drop out, and on the right I have negative 18. Now I need to divide by negative 6 and reverse the symbol. Reverse that symbol right away so that you don't forget to do it. So I have negative 6 x divided by negative 6 is greater than or equal to negative 18 divided by negative 6. These negative 6 cancel out and I get x is greater than or equal to 3. Remember, this is an inequality joined by or. So the solution set for this compound inequality is x is less than negative 5 or x is greater than or equal to 3. On the number line, what this is saying is that x is less than negative 5, so open circle since it does not include negative 5, or x is greater than or equal to 3, closed circle. So all the points here satisfy this inequality, and the points here satisfy this inequality. And for our compound inequality, we're going to include all of these. Thanks for watching Educator.com.